For more physics-related videos, please subscribe. Welcome to Stellar Physics 4F. In this video, I will cover the electron-positron pair instability. As with most of the videos in this chapter, the physics in this video will heavily depend on the results found in chapters 2 and 3, mainly thermodynamic quantities from chapter 2 and energy, equilibrium, and stability criteria from chapter 3. Understanding the pair instability is not very easy, so I've rated the physics level in this video as advanced. Before we get into the pair instability, let's first review the stability criteria under Newtonian gravity. In Stellar Physics 3e, we found the general expression for the total binding energy of a star under Newtonian gravity, where this first term is the internal energy and this second term is the gravitational potential energy. A is a constant that depends on the equation of state. M is the total mass of the star. Rho sub c is the central density of the star. Gamma 1 is the adiabatic index, and B is also a constant. In Stellar Physics 3e, we also showed that the equilibrium energy is found by minimizing the total energy with respect to the density, and the star will be stable if the second derivative with respect to the central density evaluated at equilibrium is greater than 0. Combining these equations gave us that the condition for stability is that gamma 1, the adiabatic index, is greater than 4/3. Actually, that wasn't exactly true because gamma 1 may not be constant throughout the star. So the actual condition is that this quantity gamma 1 tilde has to be greater than 4/3, the pressure-weighted average of the adiabatic index. In Stellar Physics 2c, we found that for radiation-dominated stars, gamma 1 is approximately 4/3 plus beta over 6, where beta is the fractional gas pressure, so it's the fraction of the pressure that is provided by gas pressure. So we have two ways of getting pressure, one from gas pressure, one from radiation pressure. A radiation-dominated star just means that most of the pressure is coming from radiation pressure. So in this case, we expect beta to be small. In Stellar Physics 3b, we found a relationship between beta and the mass of a star if we took beta to be more or less constant throughout the star. If we then further take beta to be small, we found that beta would be approximately equal to this expression as a function of the mass of the star. So again, m is the total mass of the star. This just means one solar mass. And mu is the average particle mass in units of a proton mass. So looking at this equation, it would appear that gamma 1 will always be greater than 4/3 because beta has to be a number between 0 and 1, and in our case, it's going to be small, but even if it's small, this quantity will always be greater than 4/3, so gamma 1 tilde will also always be greater than 4/3. So under Newtonian gravity, stars must always be stable. And in general, that's actually true. What causes stars to go unstable, as we found in previous videos, is always corrections due to general relativity. Well, there's one exception to this, and that's the electron-positron pair instability, because this expression for gamma 1 does not account for the effects due to electron-positron pair production. So what is electron-positron pair production? In a star, electrons and photons are in thermal equilibrium. This is a fancy way of saying they have the same temperature. So what does it mean for them to have the same temperature? It means that they are constantly exchanging energy with one another at equal rates. Electron-positron pair production is when two photons come together, annihilate, and produce an electron-positron pair. This can only happen if the combined energy of the two photons is at least as large as the rest mass energy of the electron-positron pair. Now notice that I've written this with two arrows, one going forward, one going backwards. And that's because the electrons and photons are in thermal equilibrium. So it is also possible for an electron-positron pair to annihilate and convert into two photons, and if they're in thermal equilibrium, then the rates of photons being converted to electron-positron pairs is equal to the rates of pairs being converted into photons. And just as a side note here, there is no limit similar to this one for converting pairs back into photons because photons have no rest mass. So electron-positron pairs of any energy can be converted into photons, but that's not the case for photons being converted into electron-positron pairs. The number of photons at a given energy is going to be proportional to the energy squared divided by this quantity, e raised to the energy over the temperature minus 1. I derived this in Stellar Physics 2a. This is essentially the probability that a photon will have an energy E. If we plot this distribution, so I'm going to plot the number of photons versus energy, it will look something like this. The average photon energy will be very close to 3 times the temperature, and we're going to assume that this is much less than the rest mass energy of an electron. On this curve, the average energy is about here. And since we're assuming that the temperature is much less than the electron rest mass, the electron rest mass energy will be somewhere over here, way off in the tail of this distribution. So that means that only the very small fraction of photons that are way off in this tail have enough energy to be converted into electron-positron pairs. And in this tail, this expression can be approximated as E squared times this exponential decay. So this is because E is much greater than the temperature, since we're off in this tail here. So E raised to a very large number is much greater than 1, so we can ignore this 1. So we just have this exponential decay as a function of the energy. Now what happens if we increase the temperature? Then the number distribution looks something like this. The average energy will increase because it's just proportional to the temperature, which we've just increased. And also notice that increasing the temperature causes an increase in the number of photons at every energy. So everywhere along this curve, there will be more photons than in this curve at lower temperature. So the total number of photons will have increased. So that means that in this tail here, not only have we increased the total number of photons that have enough energy to be converted into pairs, but the percentage of all photons that can be converted into pairs has also increased. Because effectively, we've moved mc squared further to the left along this curve. So let's think about this for a second here, because there's a subtle point to notice. If mc squared is initially way off in this tail, then increasing the temperature a little bit really doesn't make a difference, because there are so few photons that can be converted into pairs that increasing the temperature a little bit, while technically it will increase the number of pairs, it's negligible. If, on the other hand, we have a very high temperature and mc squared is somewhere around here where most of the photons are, then we already have most of the photons having enough energy to be converted into pairs, and increasing the temperature doesn't really make a difference either. When does increasing the temperature have a large effect on the production of electron-positron pairs? When mc squared is in this tail but close to this steep ramp up here. In this case, an increase in temperature can lead to a very large increase, not only in the number of photons that have enough energy to produce pairs, but a large increase in the percentage of photons that have enough energy to produce pairs. So what's important to understand here is that because we're in thermal equilibrium, these rates are equal going both ways. Electron-positron pairs and photons are constantly going back and forth, but at any given moment, there is a fixed number of photons and a fixed number of electrons. However, if I increase the temperature and mc squared is in this part of the curve, then because I've dramatically increased the fraction of photons that can be converted into pairs, the equilibrium ratio of the number of photons to the number of pairs will go down. So let me repeat that. The total number of electrons and positrons will go up. The total number of photons will go up, but the number ratio of photons to electron-positron pairs will go down, even though I've increased the number of photons. Okay, we're going to come back to this, but first we have to go over how electrons and positrons are distributed. I cover this in Stellar Physics 2a. So the number density of electrons and positrons, which I'm labeling as minus for electrons and plus for positrons, because electrons have negative charge and positrons have positive charge, we found in Stellar Physics 2a to be equal to this quantity, where g is the degeneracy, which is simply counting the number of particles you can put in a given energy state. For electrons and positrons in our case, it's going to be 2, because they have a magnetic moment that can either be pointing up or down. So in each energy state, you can put one electron with its magnetic moment pointing up and one with its magnetic moment pointing down. X is what we're integrating over, and it's just the momentum divided by the temperature. So if I had put this temperature back into the integral, I could have rewritten this as an integral over momentum. Eta is the chemical potential divided by the temperature, and I've written this as eta minus and eta plus because there's a chemical potential for electrons and a chemical potential for positrons. Mu is the electron mass divided by the temperature, and epsilon is the energy divided by the temperature. As already noted, since the photons and electrons and positrons are in thermal equilibrium, they will convert back and forth at equal rates. Now, energy has to be conserved. So if we have an equal rate of photons being converted into pairs and pairs being converted into photons, that implies that the chemical potential of the two photons must be equal to the chemical potential of the electron-positron pairs. And I've written the photon chemical potentials as the chemical potential of a photon plus the chemical potential of an antiphoton, because technically in this equation, it's a photon-antiphoton pair being converted into an electron-anti-electron pair. A positron is the same thing as an anti-electron. But a photon, it turns out, is its own antiparticle. So an antiphoton is just a photon. Furthermore, photons have a chemical potential of 0. So this then implies that the electron chemical potential must equal the negative of the positron chemical potential. So I'm just going to call the electron chemical potential as phi, and the positron chemical potential will be negative phi. So what we're going to do is we're first going to do a change of variables. Instead of integrating over x, meaning instead of integrating over the momentum, we're going to integrate over the energy. I'm also going to replace eta minus plus by just plus or minus eta, where eta will be the chemical potential of the electron divided by the temperature, and negative eta will be the chemical potential of the positron divided by the temperature. So now our number density looks like this, where here I've replaced g equals 2, so that will just cancel the 2 that was in the denominator here. Now to evaluate this integral, I'm going to make use of two mathematical identities. The first one is that this fraction 1 over 1 plus e raised to the negative some quantity is equal to this infinite sum. The second one is this definition of what's called a modified Bessel function. So k signifies the modified Bessel function. There are different degrees of modified Bessel functions, and that's what nu represents. So nu is the degree or the order of the modified Bessel function. And this is the definition, or a definition, of the modified Bessel function. So if you squint your eyes a little bit at our integral, you can see how these two identities are going to come into play. This integral here looks very similar to the top part of our integral, and this denominator looks very similar to the denominator of integral. So we can massage this expression for the number density a little bit by integrating by parts and doing a little bit of algebra until we get it into a form that allows us to substitute these two mathematical identities. And this will give us that the number density can be rewritten as this infinite sum of modified Bessel functions of order 2. Now you may be looking at this and thinking this doesn't look any simpler than what we originally had, but there are a couple things to note here. First, Bessel functions are known. So the value of k2 here, which is the second order modified Bessel function, can just be looked up. Then we have this pesky infinite sum here, but we're going to make an approximation. We're going to say that we can just take the first term of this sum as long as mu is greater than 1, meaning as long as the electron mass is greater than the temperature. Now we're going to see in a little bit that actually, even if the electron mass is less than the temperature, this approximation is pretty good. So all I've done here is, instead of doing this infinite sum, I just took the term of n equals 1, and then dropped all the other terms in the sum. So now we know what the number density of electrons and positrons is. So let's go back to our board on electron-positron pair production. We have an expression for the electron-positron number density as a function of mu and eta, which really means that it's a function of temperature and chemical potential. And we can follow the exact same procedure for the energy density as we did for the number density to get a similar expression for the total energy density. If we then divide the two, we get an expression for the average electron energy as a function of temperature. And K1 is the first order modified Bessel function. Now let's test some limits to see how well this approximation holds. First, let's assume that mu is much greater than 1, meaning that the electron mass is much greater than the temperature. In this case, the average electron energy reduces to the electron rest mass energy plus 3/2 times the temperature, which is the exact result of a Maxwell-Boltzmann gas. So that's good. Now, what if mu is much less than 1, meaning that the temperature is much greater than the electron mass? In this case, the average electron energy will equal 3 times the temperature, which is pretty good. If you actually did this exactly for the extreme relativistic case, you'd get a number that was very close to 3 times the temperature, just like with the photon average energy. Those two numbers won't be exactly the same, but they'll both be very close to 3 times the temperature. Now let's do a side calculation for illustrative purposes. In Stellar Physics 2a, we found this general expression for the pressure, where P is the momentum, E is the energy, and this plus or minus refers to whether we're talking about bosons or fermions. If it's bosons, it's a minus, which is where this minus comes from for the number density of photons. And if it's fermions, it's a plus. I'm again going to do a change of variables and rewrite this integral as an integral over energy instead of an integral over momentum. And now recall that we had this general expression for the number density. In the previous board, instead of integrating over the energy, I was integrating over epsilon, which was the energy divided by the temperature, which resulted in there being a temperature cubed factor out here. But this is the exact same integral. Now, these expressions for the pressure and the number density are the total pressure of the system and the total number density of the system. If I get rid of these integrals, then I'll have the pressure and number density at a specific energy. And if I divide the two, and assume we're talking about electrons, then I'll have the pressure provided by electrons of a given energy times the number of electrons. So this number in the parentheses is essentially the pressure provided by one electron with energy E, and then I'm multiplying by the number of electrons with that energy to get the total pressure provided by all electrons with energy E. I can do the same thing for photons, but for photons the only difference is I have no rest mass. So in the case of photons, the pressure provided by a photon of energy E is 1/3 the energy. Now let's go back to electron-positron pair production. Remember, if we're in this part of the curve, increasing the temperature will result in a net increase in the number of electrons versus the number of photons. So if I subtract these two terms, I will get the net pressure change as a result of increasing the number of electron-positron pairs versus the number of photons. And this number is always negative. So that means there will be a net decrease in pressure. Now for photons that are extremely energetic, such that they are much greater than the rest mass of an electron, this number will be very small and will be rather insignificant. This is just telling you how much pressure you lose at a given energy for each electron-positron pair you produce. Now there's a further effect here, which is that because we're in this part of the tail here, which has an exponential decay, most of the electrons being converted will be very close to mc squared, which will make this factor as large as it can possibly be. Remember, E can't be less than mc squared because you need at least mc squared versus energy to convert your photons into pairs. Now you might be thinking, wait a minute here, this is only for when you're converting photons into electrons. But we have electrons also being converted back into photons. Yes, that's true. But remember, what happened when we increased the temperature? When we increased the temperature and mc squared was close to this large ramp up here, there was a large increase in the number of photons that could produce pairs. And so the equilibrium ratio of number of photons to number of electron-positron pairs went down, meaning there's a net decrease in how many photons there are per electron-positron pair. So by increasing the temperature, we have a net decrease in pressure. Now, what happens if you decrease the pressure in a star? Well, the pressure was supporting the star against gravity. You decrease the pressure, the star contracts. Now, normally, that's not a big deal. The star contracts, temperature goes up, the pressure goes up, it puffs back out, the star stays in equilibrium. But in this case, the star contracts, the temperature goes up, that means even more electron-positron pairs are created, And so instead of the pressure going up, the pressure goes down even more, contracting the star even more, increasing the temperature even more. And again, that increase in temperature, instead of providing more pressure, just provides more electron-positron pairs, and the star continues to collapse. So we have runaway collapse. And in a nutshell, that's what the electron-positron pair instability is. If the star gets to a temperature where it starts to produce a lot of electron-positron pairs, you get a drastic drop in pressure and a runaway collapse. If you're finding this video interesting so far, please like and subscribe, and consider sharing it with a few friends. That's a nice qualitative picture of what's going on, but we still have this issue that stability is governed by the adiabatic index. Originally, we had this expression for gamma 1 being 4/3 plus a little bit, but as we said, this ignores the effects of electron-positron pair production. So this expression doesn't actually hold if electron-positron pair production is significant. So what is gamma 1 if you account for pair production? Well, it turns out that if you account for pair production, gamma 1 is equal to 4/3 plus beta over 6 times this function f of nu and mu. So really, this is a function of chemical potential and temperature. And it turns out that this function is this big complicated mess, where Z is the average charge of a nucleus and E bar is the average electron energy. Well, we already found what E bar is, so we can substitute that in. Where on earth does this function come from? In this video, I'm taking more of a qualitative approach to understanding the pair instability, so I'm not going to derive this. It's a pretty complicated derivation, but if you want to know where it comes from, you can find its derivation in this paper by Sato, or Sato. I'm not sure how that name is pronounced. It's a Japanese name. If somebody knows the correct pronunciation of this name, please let me know in the comments. So now we have a correct expression for gamma 1. And a condition that if gamma 1 drops below 4/3, the star will go unstable due to pair production. So what does that mean? That means that this function f, if it goes negative, gamma 1 will go below 4/3, and we have instability. So we have to find when does f go negative. To actually know the value of f as a function of temperature, we still need to know what eta is, meaning we have to find the chemical potential of the electrons. So let's do that now. By charge neutrality, we have that the number density of electrons minus the number density of positrons must equal the number density of protons. This is just saying that the net charge of the star has to be 0. Well, the number density of protons is the mass density divided by the average mass of a nucleus times the average charge of a nucleus. So A times MP is the average mass of a nucleus. A is the atomic number. It's the number of protons and neutrons in a nucleus. And then Z is the average charge of a nucleus, meaning how many protons are there in that nucleus. If you've been watching this series, you'll know that Z over A is generally written as YE, and it's called the electron fraction. The number density of electrons and positrons, we already found what that is. And notice here that the only difference between electrons and positrons lies in whether this is a plus eta or minus eta. Everything else is the same. So when we plug everything in to this equation here, we get the following equation. E to the eta minus e to the negative eta, if this were divided by 2, that would be the definition of sinh of eta. So we can multiply and divide by 2 and rewrite this as sinh eta. In Stellar Physics 3b, we found a relationship between the density and the temperature. This wasn't exactly the relationship. It depended on beta, which if you recall was the fractional gas pressure. But if we assume that beta is small, that expression reduces to this one. So now, all we got to do is solve for eta, after plugging in rho equals this expression. And remember that the temperature is proportional to 1 over mu, because mu is the mass divided by the temperature. So now we have eta as a function of the mass of the star and mu, essentially meaning we have it as a function of mass and temperature. This means that our function f of eta and mu will now be a function of mass and temperature, or mass and mu. Okay, now we have everything we need to find the electron-positron pair instability. We have a criteria for instability in terms of gamma 1, we have an expression for gamma 1, and we found what eta is. And our criteria for instability now is that this function f, which will depend on the mass of the star, and mu, has to be less than 0. I've made a plot of F as a function of temperature for a 100 solar mass star and a 300 solar mass star. And I took Z to be 1 just for this example. So F is on the vertical axis, and the horizontal axis is the temperature in units of 10 to the 9 Kelvin. So that's what T9 means. First thing to notice here, at low temperatures, F will go to 1 and will decrease linearly with temperature. So that's good. We needed F to equal 1 when pair creation was negligible. Remember that mu is the electron mass divided by temperature. But then, somewhere around 10 to the 9 Kelvin, you get a rapid drop in F, and it will go negative. Now, there's another thing that's important to observe here. F will go negative at a lower temperature for a higher mass, meaning that a higher mass star will hit the pair instability at a lower temperature. But then, if you increase the temperature, F will go positive again at some point, meaning that the star has a chance to go stable again if you increase the temperature sufficiently. But not only do higher mass stars hit the pair instability at a lower temperature, they become stable again at a higher temperature. So for lower mass stars, the window of instability is shorter. So now the question is, what happens when you hit the pair instability? Well, what happens is called a pair instability supernova. Maybe. So here we have a plot by Hager et al. These are the results of simulations of the outcomes of stars of given masses and given metallicities. So on the horizontal axis, we have the mass of a star in units of solar masses, and on the vertical axis, we have metallicity, meaning how many heavy metals does the star contain. By heavy metals in this context, we typically mean nuclei higher than helium. Essentially, the vertical axis is just looking at the composition of the star. At stars lower than 10 solar masses, we have a white dwarf. Then we have various different types of supernovae. This is not relevant to this video. These white areas here are not supernovae. Instead, we have direct collapse to a black hole. The area we care about is this area here in this sort of reddish-brownish color. As you can see, here we have a pair supernova and no black hole. So what happens with the pair supernova? The star hits the pair instability, it starts to collapse. As it collapses, it gets hotter and hotter, which increases the nuclear production rate, and nuclear production rates are typically highly nonlinear, so increase in temperature can lead to a very large increase in nuclear energy being released. And for masses between 140 to 260 solar masses, that increase in nuclear production rate blows up the star. But it only does so if you don't have too many heavy metals around. If the star is larger than 260 solar masses, you still hit the pair instability, but remember you hit it at a lower temperature, so not only does your temperature start off lower when you go unstable, but you have a larger mass, so in this case, the increased nuclear production is not enough to turn around the collapse, and the star collapses directly to a black hole. If the star is smaller than 140 solar masses though, so over here between 100 and 140 solar masses, you get what they're calling a pulse pair instability supernova. Alright, so let's recap. We have a theoretical prediction for the electron-positron pair instability. We have simulations that suggest that for certain mass ranges and low metallicity stars, this will result in a supernova. But, as always, does this agree with observation? Have pair instability supernovae ever been observed? Well, maybe. There's about half a dozen to a dozen supernovae out there that various people have claimed match a pair instability supernovae. But in all of those cases, those claims have been debated by others who are not convinced. So maybe some have been observed, but it's inconclusive. If you enjoyed this video, please like and subscribe and hit the bell to be notified when more videos come out. In the next video, I'm going to explain why stars, despite being some of the hottest places in the universe, are actually giant freezers. Thanks for watching.